Hi, thank you for watching our webinar. We experienced some audio issues in the first couple of minutes, so I'm here just to give you a quick summary of what we talked about in that part. So my name is Rafaela. I'm a part of the commercial team here at Gatehouse Satcom. I also facilitate the internal-external communication. So if you have any questions, you want to share your thoughts, or you just want to network, feel free to reach out to connect. I'm going to be happy to engage. So together with me today, I have my colleague René. He is a research engineer here at Gatehouse Satcom. He's also heavily involved in the development of 5G Narrowband IoT NTN, but 5G in general as well. So it's great to have him in the discussion today. So a quick introduction for those of you who are just coming across us right now. So Gatehouse Satcom, we are a software dedicated company. We've been doing software for satellite communications for the past 25 years. From these 25 years, the past 5 marked the beginning of our 5G NTN journey. And that means that we joined 3GPP, we're active members there, helping to define the standards. And we also developed our full 5G Narrowband IoT protocol stack from scratch. And we're also taking the first steps into 5G new radio, focused on the physical layer, which is our expertise here in the house. So that's very exciting. I'm now going to lead you to the webinar per se. We're going to start diving into the use cases. And after that, René is going to explore a bit more of the technical requirements for the ones we selected, which are push-to-talk, firmware updates, and two-way messaging. I hope you enjoy it. And yes, see you around. Bye. For the use cases, they're widely discussed in the market for some time now, but they're still being very much discussed. And usually the discussion goes around what we called the classic IoT cases. That in examples that I was mentioning, is, for example, asset tracking for remote locations, for the industry, maritime industry, mining, places where there's no coverage from terrestrial networks. There's also asset tracking. It could be for tracking people, animals, or objects in general. There are many different examples for for the classic IoT cases, and but beyond that, let's have a look now then into the last discussed cases that are outside of IoT. That through our research, we saw that there's a very big potential there, and it's a very good opportunity. It's great news for those who are investigating Narrowband IoT NTN as a possible technology for their business, or for those who are already implementing it, so that they can offer even more value and functionalities to their end customers. So then I'm gonna pass the word to my colleague René, so he goes through the technical requirements for the cases.
Services. Thank you, Rafaela. So I'm happy you can all hear us now. As Rafaela mentioned, we are looking a bit today into some use cases which are pushing the limits more of NB-IoT than a simple mobile originating message of a few bytes, a reporting message would be. And those services are, to go quickly over them, two-way messaging, push-to-talk, and over-the-air updates. I will be presenting the use cases, the technical requirements, and how it could be implemented, and then going over some results based on our evaluations throughout the presentation. And I'll do so for 3 different constellations: LEO, MEO, and GSO, where the LEO satellite or the LEO constellation would be at a height of 600 kilometers, MEO at 10,000 kilometers, and GSO in the geostationary orbit. There are some round-trip times associated with each of those constellations, and we have chosen to use the worst case round trip time for both the service link and feeder link, corresponding to UEs and ground stations at about a 10-degree look angle or elevation angle in most of the cases. So that's, let's say, the short overview of what we're going to talk about. And then let's start off with the first use case of two-way messaging. Here we are talking about it's a pretty basic use case, but here we are talking about quite large message sizes, so 160 characters, and also the constraint of a delay which may not exceed 10 minutes. So you should be able to transfer a message and receive an answer which both are 160 characters within 10 minutes of time. And at first, we have evaluated this in an outdoor scenario with line of sight link conditions. Yes.
No, it's just a question about the devices.
Yes.
So all standardized devices in the future, will they be able to have access to this functionality as well?
Yes, the functionality we have on the next slide. What is required to do this two-way messaging is simply utilizing the control plane optimized data transmission, or data ONS, as it's known popularly amongst the technical people, I guess.
Mm-hmm.
But data ONS or DONS exchanges are mandatory for UEs to support. So every single device from release 17 and up that supports NB-IoT NTN will support this feature. So the exchange is depicted on the figure here. It's a random access preamble, a random access response, a connection request and setup, and then the connection complete message. And those are normal control messages on which you piggyback the data. So the data can be piggybacked on top of the connection setup, the connection complete messages. In any case, for our evaluation, what we have done is to consider the link level performance evaluated through link level simulations of NB-IoT signal, reception, transmission and reception, including NTN fading channel. The environment is rural, outdoor line of sight as mentioned. We consider a single tone 3.75 kilohertz uplink transmission or uplink transmissions. And then based on those evaluations, we have evaluated on top of that on a more system level, so a MEC scheduler level, how are we able to schedule things and how long is the propagation time and so on, in order to figure out if we can do these transmissions within 10 minutes. So the further conditions of the system evaluation are that we have picked some SNR points. They will be clear from the next page with the results. But sorry, we can say it. But the downlink SNR is chosen to be 6 dB lower than the uplink SNR. And in our experience for NB-IoT, 6 to 8 dB is a reasonable margin for many cases out there. But of course, it's individual from the satellite constellation, satellite payload to payload. What would be the number? So the scheduler implemented is choosing the transport block segmentation based on how it can use least resources in the system or to minimize time on air, basically. So it doesn't take into account propagation time, which is also something to keep in mind, because you could, in theory, support these use cases with less delay if you take into account propagation time. We include a co-op header next to the payload, or with the payload of 160 bytes. And then our fading model that we evaluated was for 10% block error rate. So we have also introduced errors and HARC retransmissions in our evaluation. In any case, we use this control plane optimized data over NAS transmission exchange. And with all of this setting in mind, we have evaluated some results, which are shown here in the tables for LEO, MEO, and GSO constellations, and for different SNR points. They are evaluated for the regenerative architecture that is a full eNodeB onboard a satellite access node on the left, and on the right you will see the total exchange times for a transparent payload. So two quick conclusions here is that the exchange time, even in the poor link conditions of having -5 dB SNR in the uplink, which corresponds in our settings to a -11 dB SNR in the downlink, even in those conditions, we are able to do this transmission of 160 bytes back and forth. So from a mobile to a server, and from the server to a mobile, in tens of seconds. So at most 20 seconds, as you see in the GSO case, for the regenerative architecture, and 26 seconds for the transparent payload GSO. In good link conditions, we can obtain very large gains. Of course, better link conditions means the total exchange time goes down, and we see that it's in the order of a few seconds when we are up to 5 dB in the uplink, and what would be -6 dB in the downlink in this case. -1 dB in the downlink in this case, sorry. Another quick conclusion is that LEO doesn't suffer from as much propagation time as GSO, which is why we see LEO, of course, being able to finish the exchange quicker. And since GSO suffers more from propagation time, the gain of going to a transparent architecture is larger in this case for this architecture. So two pretty simple tables, I would say, as a result from what was a big evaluation for this. But as we go on to our next use case, we will reuse the setting that I explained before in the schedule. So this next use case is push to talk for voice messaging. The use case, the scenario here is that we want to be able to have a push to talk service via the satellite. We want to be able to record and receive voice messages of up to 30 seconds. The delay from we release our recording button to it is received should not exceed more than 1 minute. And again, we're in the outdoor line of sight environment. So on the next slide, I have listed basically the same settings as for the other case. We rule outdoor single tone transmissions in the uplink. We have 10% block error rate target for our transport block selection in the scheduler. How is enabled? The downlink SNR is 6 dB lower than the uplink, and the scheduler is choosing the transport block segmentation based on what will use the least time on air for the transmission. So all the setting is the same, the scheduler, the evaluation part, it's just that our traffic pattern is a new one. we're still using the DONAS transmission format to do this. So, in order to transfer speech, we need to encode the speech. So there's a codec called Lyra, made by Google, developed by Google, which can encode lossy speech, meaning that it will lose some of the information in the original audio signal, but we think that Lyra is quite good at maintaining the, how do you call it, the speech itself. And that can be done at 3 to 4 kilobits per second, 3 kilobits per second. But if we assume a worst case of 4 kilobits per second, a 30-second audio clip would be 130 kilobits. That is quite a bit from the 160 bytes we wanted to transmit before. So now we're really going to try and push the boundaries here. I think we can listen to the samples of how Lyra sounds, just to get an idea about how the something implemented with this use case would sound like. So we have a sound bit here. Let's play a few seconds.
And this is the original speech.
Original sound speech, yeah.
That we're gonna play.
The north wind and the sun were disputing which was the stronger, when a traveller came along, wrapped in a warm cloak.
I think that's fine.
They agreed.
I hope you were able to hear this. Then let's play a few seconds of the Lyra encoded at 3 kilobits per second. Counting file.
The north wind and the sun were disputing which was the stronger, when a traveller came along, wrapped in a warm cloak.
Okay. So that's kind of the quality of the use case. So that's our first trick, let's say, because of course, going for voice in high quality over NB-IoT is not feasible. So doing this actually makes it into a feasible use case. Still, we're pushing the boundaries. And when we go to the results of our evaluation with our scheduler and link level performance results, we can see that in good link conditions, this threshold of 60 seconds can be supported. So in our figures here, we are going to have regenerative use case on the left and transparent use case architecture on the right. There are 3 SNR points plotted, an uplink SNR of -5 dB, 0 dB, and +5 dB in black, red, and blue each. And if you look at the blue one, which should be the good SNR conditions, you can see that in MEO and LEO, you are able to support this push-to-talk service with a delivery of a 30-second message within 1 minute at an SNR of 5 dB. So in the good link conditions. However, if we go to poor link conditions, we're not able to. And the same story as last time repeats. MEO and GSO has longer propagation times, and therefore we are taking longer to finish the entire exchange of messaging. So for those cases, it pays more to move from the transparent to the regenerative case. And also we see that compared to Leo, they are performing worse, or they're taking longer to go through the entire exchange. What else can be said? Yes, of course, if this is supposed to guarantee that you can transmit messages to someone who's not in very good link conditions, you can still do so, although you will arguably have to either live with a longer delay than 1 minute, say for instance 2 minutes or a 3-minute delay on the voice messages, or you would have to say that the voice message length is limited in time, so only maybe 1 to 5 seconds of transmission time. Okay.
I have a commercial question.
Yeah, of course.
So I read that with push-to-talk, one is able to send the same message to a group of people. It doesn't have to be, just send my message to another device. No, I can actually transmit / send my terminology, but to a group of people. Is that feasible in that setting?
Yes. So what has been evaluated here is for this control plane optimization, the data over NAS transmission or message exchange. This is mandatory for all UEs to support. There's also a feature called multicast, or point-to-multipoint, single carrier point-to-multipoint in NB-IoT, which is not a standard feature. But UEs that support this feature could have broadcasts of the information. So here, let's say we have evaluated transmitting a message from one UE to another, but transmitting the message from one UE to a group should be similar, except for the broadcasting to the group part.
Okay.
And the use case we're going to talk about now, firmware updates, relies entirely or heavily on the feature of multicast. So it's a good bridge.
Thank you.
So the next or the last of the use cases we are discussing today is the over-the-air updates. Now, since you just asked, here we're using the multicast feature, or at least I am in the evaluation, but you could also update individually UEs and then rely on the results from the push-to-talk use case. As we can see here, the minimum payload that we have set for this use case is 1 kilobyte, and what we were evaluating before was the transmission of 120 kilobit.
Yeah.
So 120 divided by 8 times as much, many times as much, right?
Uh-huh.
50 times that much. So for unicast, you can rely on the results of the PPT use case. But here we will evaluate a multicast. So the threshold here is 1 week for the delivery of the update. We must include some tracking of a successful update that is a bit that can be done, but is not within the scope of the evaluation. Then we have a possibility for prioritizing services for faster updates, interrupting others, and so on. And these things I mentioned, point 3 and 4 here on the slide, can be implemented as an app-level functionality. So multicast itself is an optional feature within the communication stack of NB-IoT. And then on top of that, you can make an proprietary app, which is able to enforce point 3 and 4 here. So very doable within NB-IoT, but it's not part of the protocol itself. It's something you can do around it. On the next slide, I have the setting again. To go quite shortly, it is the same setting as before. But now, since we're dealing with multicast, what we're investigating is how can we broadcast these 1,000 bytes from a satellite to the UE or to a bunch of UEs. Now, the way to do it is to use the SCPTM, single carrier point to multipoint, on a dedicated carrier. Or not necessarily a dedicated carrier, but that's the assumption for the evaluation here. I have not considered HARC here, but I have considered that you would transmit your 1,000 bytes using fountain coding. So for instance, RaptorQ, which is a standardized protocol or encoding by IETF, which gives 1 in a million times risk that you cannot decode the original message if you just add 2 more transport blocks to the size of the original message. So let's say it's 20 transport blocks we needed to transmit. If we transmit 22 and we encode all of these with fountain coding, then receiving any 20 of those blocks, we would be able to recover the original message. Or any 22 of those blocks, we would be able to recover the message. Then we add transport blocks in order to achieve our 1 in 10,000 risk of not being able to receive those N+2, so those 20 + 2 transport blocks in that example at a 10% blocker rate for the original transmission. So with all that in mind, we evaluate again what is the total exchange time. This time we went quite a bit beyond the requirements of the use case and started to evaluate how many megabytes can we transmit in our poor, okay, and good link conditions for the threshold of 7 days or 1 week. And within a week, you can send quite a lot of information with NB-IoT, especially in good link conditions. In poor link conditions, of course, we're relying more on our repetitions. The transmissions will take longer. And when we are broadcasting, we are more likely to be broadcasting to a lot of devices where there's a higher chance that some are in poor link conditions. So we would be more likely to follow or go with the yellow or red curve here for more realistic results. But again, it depends on the satellite payloads, satellite constellation. Yes, and 3 quick conclusions here is that we can be very highly reliable for rather large transmissions within the thresholds of the use case. So as we see here, we have 350-ish, 330 megabytes or megabits, payload that we can transmit within the 7 days threshold, even in the poor link conditions. So quite large. Of course, we would be taking up a full carrier in that time, and that would be very costly. So let's say in practice, you're not going to do that. You're going to transmit way less. Maybe you'll transmit 1 megabit and then not even spend an hour doing so. And that's perfect, right, for all of your broadcasting needs. Then you would also be able to switch around. And of course, you could implement this at application level, and you could have designed a schedule of times for when UAs would be observing these broadcasts.
So there's a more cost-effective, optimal
Yes,
use of
yes.
this functionality?
Yeah, so here we were looking at doing a single transmission, a single broadcast, but in a system you would probably have more people wanting to do broadcasts. So you can do some round robin thing to switch between them. And if you have very large payload you wish to broadcast, the total transmission time may be 7 days. But if you have an application which is able to share the time with other broadcasts, then your UE will combine those informations in the application somehow. You will be able to do your broadcasting over a longer time. So it will take longer calendar time than the 7 days, but you wouldn't take up the entire system for that.
Yeah.
So that's an important consideration, I think. Here we used Raptor Q and repetitions of the transmissions in order to get extreme reliability for the broadcasts, and that's one way to do that. But there are also some hack features in NB-IoT for broadcasting. I'm not too familiar with those yet. So just for your information, I think there's something there. But otherwise, in order to obtain the reliability, you can do like this: fountain coding and repetition.
Nice.
Yep.
All right.
I think that's it from me.
Okay, that was great, very informative. Yeah, I have, before we move to the questions, I have a question in mind. So, and I imagine that's a question many of us from the commercial side have in mind as well. So we're talking narrowband IoT, and we're talking different kinds of use cases that are not only IoT. So in the market now, we talk a lot about 5G as a whole, and then 5G new radio as well. So one question that it's kind of buzzing: what is your perspective on do you think that 5G narrowband IoT will be replaced by 5G new radio? What's the let's say the benefit of 5G narrowband IoT, not against, but besides new radio, because they're in comparison, exactly, because they're different technologies. But I see this is a common question, I think.
Yeah.
So that would be nice to hear your perspective.
Yeah. So I think the communication technologies by themselves have very different use cases. NR is broadband. It allows you to transmit in what is called bandwidth parts. When you are having when you're transmitting to just one UE, you can transmit in just a little part of the entire bandwidth, which actually enables it to go towards the IoT domain, let's say, of complexity, where UEs don't have a lot of power, and they don't have a very broad filter, because it's much harder to make a receiver with a broad filter that gets in a broad channel and then is able to analyze all the information. So being able to do that in NR is very smart. But even though it can make quite narrow channels, the channels are not as narrow as those of NB-IoT. So the NB-IoT uplink is a great advantage of NB-IoT, especially in cases where the uplink is challenged, and when you have the NTN or the satellites, the link budgets are challenged. In many cases, you would be within or close to the power limited domain, even with NB-IoT. So here you can really only get better performance by either transmitting with more power, which might not be an option, or is not an option in most cases, especially for the cheaper devices. but you can go to have a smaller spectrum like you do in NB-IoT. So I think they are designed for each of their use case. And I think it's more a matter of they will play together. There may be some overlap where you can do with NR, you can also make somewhat cheap devices which are capable of the IoT part of things. But I don't think people who are aiming to make those devices will go for NR over NB-IoT due to the cost, increased cost. So plenty of trade-offs, but I think they will coexist. Yes, short result.
Okay. Thank you very much. So summing up, it's about efficiency, costs, and some overlap. And but anyways, to each their own. A common thing that René discussed throughout the use cases is that here he made some general calculations, but we have to keep in mind that they all depend on a specific system architecture or satellite configuration. So having that said, if you want to check your own system, your own setup, you are also able to do that with us. So for example, this is the kind of roadmap, let's say, that suggested that you can start with the dedicated study and validate your roadmap and then move forward with some demonstrations that can be in lab, in orbit, depending on your what's relevant for you. And then afterwards, you can confidently deploy your solution. So let's go to our questions. Now we're going to have a look into your questions. Just a second. At first, everybody was warning us about the audio. Thank you very much. While we find a question, I'm just gonna let you guys know that we're gonna try to answer the more questions we can live. I know we are quite a bit on the edge of our time here. Sorry for that. But even the questions you send now, or we're not going to be able to answer live, we're all going to answer them on written, and we're going to send together the link to the recording to today's webinar and the presentation, and you're gonna receive it all over email. So don't worry, you can send your questions. So René, can you see this one?
Yep. How can it be only 26 seconds per GSO? So that was on the first use case, two-way messaging. And I don't know if we can bring up the slide.
Yes.
Then I can try to...
This one?
Yeah.
Or do you
slide
want
7. This one.
This one.
I can try to explain a little bit, or maybe slide 8 first. Then I'll see 26 seconds is for the transparent architecture. Okay, then the slide before that. Yes, so the data over NAS transmission consists of 1, 2, 3, 4, 5 messages. And those are basically, 2.5 round trip times. The round trip time for GSO we had on the very first of my slides.
This one?
About 540, yes. So if you consider just that, it might seem more plausible to you. I don't know if it was the propagation time that was what did you weren't believing, or maybe it's the modulation and coding scheme that has been selected. But here, again, it has been based on our fading model and link level evaluations, or link level evaluations, including a fading model. And yeah, those are the results of the model.
All right.
26 seconds is
yeah.
Oh.
This one.
How many hack processes did you enable for the PTT settings? Was it in a Leo setup? So the number of hack processes is 1. There's no dual hack enabled, but that's also setting that NB-IoT has. But I just did the calculations or the evaluations with a single hack process. With dual hack, it could be faster, especially for PTT, as you are pointing out, because you would have to segment some of the larger transmissions in multiple transport blocks, and having the ability to correct one of them at a time in parallel, let's say, is faster than waiting for the correction of the serial lines. So, very nice question.
Yeah.
There's a question on the number of PTT users that can work at the same time. So again, that depends a little bit. If you were to implement it in the multicast fashion or the unicast fashion. In the unicast fashion, if you're considering the good link conditions and a short message size, you could have a capacity of 30 users per second for 1 second messages. And I've calculated about 10 users per second for a 5 second message in the good link conditions. So obviously that would go down for worse link conditions. And having 10 people being able to do the recording and transmit them at once is quite a lot. Now, instead, if you consider the multicast scenario, then it would be 10 people are able to record their message and transmit it, or actually it would be many more than that because you don't need to do the downlink direction to the other user. And then you could, instead of just transmit it to 10 people more per second, you could broadcast it to however many UEs are within coverage in the cell.
Nice. Okay, that's very interesting information.
How is it going?
Do you want to?
No.
Yeah.
But it is. Okay. There are some questions which are a bit related to today's talk, but not to the to the exact use cases. But what is the number of satellites on the LEO constellation to obtain those delays? So the number of satellites here is 1. So just considering 1 satellite being connected all the time, right? And that translates to every time the exchange time goes over, let's say, 120 seconds, then you'd be out of the window of coverage for a typical LEO satellite. Then you would need to have a big enough number of satellites that you can provide coverage for the amount of time of the length of the transmission. So I would say it takes a single satellite up till the point of 120 seconds, and then you need to have satellites enough to provide coverage, continuous coverage all over the Earth.
That's good perspective. I think for the last question, because I know we're after time. What do you think about this one?
It's a long one. Okay, another important question: are the messaging services and the push-to-talk services still supported for mobile on the move when GNSS signals are jammed? In release 17, the answer is no. There is no way to do that when your UE cannot maintain or does not know its own position, and especially if it's moving. It would interfere with other transmissions in the uplink. If it cannot know its own position, it cannot precompensate properly for the frequency shift of the Doppler from the satellite moving, right? So it could, in theory, work for GSO. It doesn't work in release 17 because it's banned. In release 18, there are features such that you can maintain connectivity even after having a GNS being jammed, but you can only do it for a short while. So release 17, no. Release 18 depends for a short while.
Okay, then I think we're about the time. I want to thank you all for your presence, for being here today, for sending the questions, participating, also letting us know about the audio and everything. And yeah, if you want, you can reach out to me. You can reach out to René. We can connect on LinkedIn and continue the conversation. Okay, then have a good day or afternoon or evening, and hopefully see you at the next webinar. Bye.
Bye-bye.